So these are the structure questions related to exercise acid-base equilibria. The first two questions are already recorded, so we'll start with question 3. So we completed this topic, the explanation yesterday, so I prefer to solve the question related to the topic after explaining. So propanoic acid is a weak acid. Define the term Bronsted-Lowry acid. Like, what is the definition of acid? Acids are known as the proton donors. So any chemical which donate proton, we call them as acid. Next is, what is the pH of 0.1 mole per dm cube solution of a hydrochloric acid? Because hydrochloric acid is a strong acid, and how would the pH of any weak acid of the same concentration differ? So how we know the concentration? Because it's a strong acid and strong acids ionize completely. Like hydrochloric acid dissociate into H plus ion and Cl minus ion. If this is 0.1, this will also be 0.1, the same concentration. Because complete dissociation is there for the strong acids. So the concentration of using the concentration of hydrogen ion, we know pH is equals to negative log of the hydrogen ion concentration. So minus log of hydrogen ion, which is 0.1. So we substitute, we'll get the pH of the solution, which will be 1. Because negative log of 0.1 is equals to 1. Then what we expect for a weak acid, so for a weak acid, we expect the pH will be higher, like it will be greater, but higher than 1 according, like if it's a strong acid is 1, pH definitely will be greater than 1, but it will be less than 7. So we expect the pH maybe 4, you can say 5, but you cannot say 8 because 8 will be alkaline. Is it clear discussion? Any doubt in the part B?
No, sir.
Okay. In part C, methanoic acid was mixed with propanoic acid. Look, when you mix the two acids, then the one which is having a higher value of a dissociation constant, that will act as an acid, the other will act as a base. Use your data booklet to decide which acid is stronger. I will state the value for the, like when you check the data booklet, the dissociation constant for methanoic acid is 1.64 into 10 power minus 4. That is the dissociation constant for methanoic acid. And when you check a propanoic acid, the dissociation constant for propanoic acid is 1.4 into 10 raised power, 1.3 into 10 power negative 5. So which is having a higher value of a dissociation constant? Is it methanoic or propanoic? Which is a high value? So which is having a high value? So methanoic acid value is higher. So which is a strong acid? It means the methanoic acid is having, it's a strong acid because it has a greater value of a dissociation constant, or it was having a higher value. You can also compare Ka also, pKa. Remember one thing, the relation between pKa and K, like this is a dissociation constant. But when we work out the pKa, if a dissociation constant is higher, the pKa will be smaller. So the pKa for this one will be 3.8, and the pKa, when we take negative log of Ka, we got 4.9. So when it is about pKa, the one which is having a higher pKa, it's a weak, and the one which is having a lower pKa, that is strong. But in terms of dissociation constant, the higher value for dissociation constant means most of them break down into ion. In part C2, hence complete the following equation. So as we identify that methanoic acid is a strong acid compared to propanoic acid. So methanoic acid should lose proton. And for carboxylic acid, they will lose a proton, which is there at the end. So this proton will be lost and the other should gain that proton. So what will happen if there's a loss of proton? This proton will be lost. So it will be HCO and this proton is accepted here. So this will be C2H5COO. H2 will be there, and this will have a positive charge because it gained proton. Overall, both molecules were neutral initially, but one has lost proton, another one gained proton. That's why that is one will get a negative charge with loss, and the other will be positively charged. Then calculate the pH of a solution of 0.05 moles of sodium hydroxide. Sodium hydroxide is a strong base. So sodium hydroxide, which is a strong base, so strong acid and strong base ionize completely. That's a definition. So it will dissociate into sodium ion and the hydroxide ion. If let's say this is not for sodium hydroxide, but let's say it was 2, so then we will write 2 here. But this is 1, so it's 1. So if 0.05 moles are the concentration is there, same number, same concentration for sodium ion and same concentration for hydroxide ion. And we have the formula, the product of H plus concentration and the OH minus concentration will always be 1 into 10 to the power minus 14. But this is a conditional at 25 degrees centigrade. When it's 25, then the product will be 1 exponent minus 14. And the solution, the sum of pH plus pOH will be 14. So using this, we can work out the hydrogen ion concentration. So hydrogen ion concentration will be 1 into 10 to the power minus 14 divided by the concentration of OH ion. So it will be 1 exponent minus 14 divided by the concentration of the OH ion. The OH ion in this, it is 0.05. That will give us a hydrogen ion concentration. And using the hydrogen ion concentration, so this value will be 2 into 10 to the power minus 13. And now we need the pH. So pH is equals to negative log of the hydrogen ion concentration. So pH will be equals to negative log of the hydrogen ion, which is 2 into 10 to the power minus 13. So when we simplify, the pH of a solution will be 12.7. That is the pH of this solution. Is it clear, this one? How to work out the pH of a strong alkali?
Yes.
Yes, sir.
Okay. Now, a buffer solution question. Usually, how a buffer solution is there when a weak acid is mixed with the salt or weak alkali is mixed with the salt. And or sometime we have a weak acid and we have a limiting reagent alkali, or sometimes we have a weak alkali and a limiting reagent acid. So that will also result in a formation of a buffer solution. Now the question is, a buffer solution was made by mixing 20 cm cube of 0.05 mole of sodium hydroxide with 20 cm cube of 0.5 moles of propanoic acid. And so how this will be a buffer solution, and we want to write an equation between a reaction of sodium hydroxide and propanoic acid. So propanoic acid, it was C2H5COH written and reacted with sodium hydroxide. So sodium will take position of a hydrogen. It will form sodium propanoate, the salt, plus water will be there. Acid react with an alkali. Its state symbols are not required, but if you write acids are aqueous, alkali is also aqueous, salt, a soluble salt will be aqueous, and water will be a liquid state. But they did not ask for the state symbols. And a propanoic acid, we already in the data booklet we already know the Ka, the dissociation constant, which was 1.3 exponent minus 5. We will use that to work out the pH. How we can use it? So this is an equation for us. So remember the dissociation constant. We use the same formula. Dissociation constant is the product divided by, we write a dissociation constant for the acid. So here the propanoic acid is there. The propanoic acid is C2H5COH and it will dissociate into C2H5 propanoate ion. and the hydrogen ion. So if we write the Ka here, because using the concentration of hydrogen ion, we can work out the pH of the solution. So if we write the Ka, it will be C2H5CO, the hydrogen ion, the product divided by the reactant, which is the concentration of acid C2H5COH. Ka, from where we get the Ka? Ka is already, the data booklet is there, so we will have that value 1.3 to next power minus 5. So we have the Ka. This is with us. Hydrogen ion concentration we need. That is the unknown. Another thing is the concentration of acid and the concentration of propanoate ion. So the concentration of the propanoate ion will be same as the concentration of the alkali, because alkali is a limiting reagent. Sodium hydroxide, like how much sodium hydroxide is there, same number of moles of sodium propanoate will be produced. So using that, we can work out the concentration of the salt, the propanoate ion, because this will dissociate into what? It will dissociate into C2H5COO negative and Na positive. So this negative ion is due to the sodium propanoate, and sodium propanoate is formed because of sodium hydroxide. And the concentration of acid, this is not the original concentration of acid, this is the concentration of acid which is left, like new concentration, because originally the concentration of acid was 0.25, but we are not left with 0.25 as the acid some of the acid has reacted with an alkali, so definitely the moles will change, so as a concentration, and the total volume will also change. So if I write the equation again, like C2H5COOH was reacting with sodium hydroxide to form sodium propanoate plus water. First, we'll find the moles of sodium hydroxide. So moles will be concentration into volume. The concentration is 0.05 and the volume is 20 divided by 1000. So how many moles of sodium hydroxide are there? 0.05 times 20 divided by 1000. 0.001. Okay. So it is 0.001 moles are there for sodium hydroxide. And how many moles of propanoic acid is there? So C2H5COH, that is the concentration into volume. The concentration is 0.25 and the volume is 20 divided by 1000. So 0.25, if we have 0.25 multiplied by 20, and then that is divided by 1000. So we got 0.005. These are the moles which are used. And the ratio between them is 1:1. 1 mole will react with 1 mole. So sodium hydroxide is a limiting reagent. If 0.001, how many moles will be there? How many moles will be reacted? So 0.001 will react. But then how many are left? Because these are the total moles and these are the reacted moles. So how many moles are left? 0.005 minus 0.001. So we are left with 0.004. So 0.004 moles are the one which is left. Same thing. How many moles of sodium propanoate will be produced? We take a ratio between sodium hydroxide and sodium propanoate, 1:1. So 0.001 moles will be produced. But we need a concentration, because whenever square bracket is there, it means you have to substitute concentration, not the mole. So how we find the new concentration? If we want the concentration of sodium propanoate or the propanoate ion, it's the same thing. So if we need a concentration, concentration is moles divided by volume. How many moles are there? 0.001. But what about the volume of the solution? The new volume of solution is 20 and 20. Like 20 cm cube of alkali is added to 20 cm cube of an acid. So the total volume will be 40 cm cube. So if the total volume is 40 cm cube, so what you have to do? You have to divide it by 0. So you have to divide it, 40 divided by 1000, so 0.04. What is the answer here? So if we have 0.001, which is divided by 0.04, so we got a concentration which is 0.025. So this is we got the concentration which is 0.025. Then we need the new concentration of acid because not all of the acid is used up. Some acid is still there. So now the new concentration of propanoic acid, C2H5COH, again, the concentration will be moles divided by volume. So 0.004 moles and divided by 0.04. So 0.004 was divided by 0.04. That will give us the new concentration, which is 0.1. Now we just substitute the values. Like the K is a dissociation constant, which is 1.3 into 10 to the power minus 5. The concentration of the propanoid was 0.025. The concentration of acid was 0.1. And the concentration of hydrogen ion is unknown. That is what we are finding. So just cross multiply. Like 0.1 will be multiplied and 0.025 will be divided. That will give us a concentration of hydrogen ion. And after finding the concentration of hydrogen ion, we'll find the pH by using a formula. pH is equals to negative log of hydrogen ion concentration. Is it clear, the structure of the question, that how it can?
Yes, sir.
Okay. Next is look for acid and alkali, like the buffer solution. I advise that you learn the structure of this answer. This is a repeated and a common question, that when a small amount of acid is added or a small amount of alkali is added to a acidic buffer solution or alkaline buffer solution, try to learn the structure of the answer. So the question is, explain how the solution act as a buffer when a small amount of alkali is added. Include any relevant equation in your explanation. Look what we have in this buffer solution. Buffer solution is a mixture of weak acid and a salt. So we have a weak acid, which is C2H5COH, the propanoic acid, and that will partially dissociate into C2H5COO, or negligible dissociation is there. And we have its salt, which is C2H5COONA, and because it will dissolve, so it will completely dissociate into C2H5CO and Na positive. And as we know, we wrote the dissociation constant, like it was the concentration of the C2H5CO negative and hydrogen ion positive divided by C2H5COOH, the acid. If the hydrogen ion concentration, so it means the hydrogen ion concentration will be equals to the concentration of acid C2H5COH divided by the concentration of the ion in the salt C2H5CO negative into K. So K is a constant thing, like it depends on temperature, but as the temperature does not change, K does not change. So which factor can affect the hydrogen ion concentration? This ratio can affect the hydrogen ion concentration. So because we have like plenty of the negative ion, like as you can see, one is from the acid and another one is from the salt. So we have excess of this negative ion. So even like example, when we add a small amount of alkali, we add OH. Say this ratio was, if I give a number, so this ratio was, this is already more because it's a molecule of acid. Let's say this was 10,000. And this will also be greater, like maybe that is also, say 15,000 example, or 2,000 example. So what will happen when we add a small amount of alkali, the OH, that OH will react with the hydrogen ions and it will shift the equilibrium towards the right hand side. So when it will shift the equilibrium towards the right hand side, so means this will decrease and this will increase. But the increase and decrease when a small amount is added, like it was 10,000, maybe now it will become 9,999. And what will happen to this? This will become 2001. So the ratio, negligible change in the ratio, like one is increasing, other is decreasing, But because the numbers are so large that 1 or 2 or 1,000 or 10 or 50 does not make much difference to the ratio. That's why the hydrogen ion concentration does not change. So the pH does not change. But how you write the answer, as I mentioned, try to learn the structure answer for this. So first thing, whenever you see a question about acid buffer, you'll mention there's a large amount of or a reservoir of a conjugate base, you can say. Conjugate base is this. This is because this is acid, so this is a conjugate base. So you can say we have a large amount or a reservoir of a conjugate base. That is one thing. Like we have acid and a conjugate, both are in large amount. This is because it does not dissociate, and this is because the salt will dissociate completely. So large amount of, so you have to mention this, that we have a mixture which contain a large amount of the acid reservoir or a large amount of acid and its conjugate base. Or you can also say salt. That is 1 mark. Then when we add an alkali, if we add an alkali, the alkali will combine with the hydrogen ion. So as a result, it will form propanoic acid. And propanoic acid is a weak acid because when small amount of alkali is added, the OH ion will react with the hydrogen ion. And it will shift the equilibrium towards right. So it will produce us, the negative ion is there. So the pH, why the pH remain unchanged? Because the OH is like the addition of the OH is removed by the hydrogen, because hydrogen combined with OH and it produce another, shifting the equilibrium towards the right hand side. So the ratio will change, but we say ratio hardly change. So how you score 3 mark? 1 mark you'll mention we have a reservoir of acid and its salt, 1 mark. Then the second mark, when we add OH, it will combine with a hydrogen ion. And as a result, the equilibrium shift towards the right hand side. So more propanoic acid will dissociate. And the third point will mention that the ratio between the acid, the concentration of acid and the concentration of a salt hardly changes. That's why the pH does not change. Is it clear, the structure of the answer?
Yes.
So try to learn the structure of, especially for this answer. Another question related to acid-base equilibria, question 4. Ethanoic acid is a weak acid and it is found in vinegar. Successive replacement of methyl hydrogen atom by chlorine atom gives. So we have a chloroethanoic acid, we have dichloro, trichloro. Explain the term weak and the acid. So how we define the term weak? Weak is refers to dissociation and acid is refers to loss of anything which gives out proton. So we'll say why it is weak. We'll say dissociate or ionize partially. And why it is acid? Because it donate proton. Don't say hydrogen ion, because hydrogen ion can be positive or negative. Or if you say denote H plus ion, that is fine. But don't say hydrogen ion, as hydrogen ion can be positive or negative. Write an expression for dissociation constant for dichloroethanoic acid. If the dichloroethanoic acid is dissociated, what will the expression for that? Because acids are proton donors, so they will always donate or give out proton. Means the equation, if we write the equation, they don't ask for equation, I'm just writing equation to write an expression for that. So if we have a dichloroethanoic acid, it will dissociate into CH, Cl, CO negative and H positive. So if we need the dissociation constant, so it will be Ka, the product, which is CH, Cl, COO, hydrogen ion, and divided by CH, Cl2, COH. Use K of the data booklet. 4 acids are to place 4 acids name into in order of increasing the strength, and how the order they have can reduce from K data, like the strong and the weak. So how it can be done? you have to use like ethanoic acid is there and one monochloro or chloroethanoic acid, dichloro, trichloro. So we have to use a data booklet for all of this. So what will happen? The one which will have a higher value of a data booklet, that will be the strongest. If K is higher, look, two things are different. We compare Ka, the one which will have the higher Ka, that will be a stronger. Or the pK, one which is having the lowest pK, that will be the strongest. Because the relation between Ka and pK, it is inverse. If the K is higher, the pK is lower. Same concept as pH. pH is negative log of hydrogen ion concentration. So if there are more hydrogen ion concentration, so the pH will be lower. So the one you will see the data booklet value, either a pK value. So when you look for pK value, look for the one which will have the smaller pK value, that will be strongest. But if you are looking for Ka value, the one which is having the highest Ka value will be the strongest. So that has to be done by using a data booklet values from page 18. The pH of a solution, calculate the pH of a 0.1 mole ethanoic acid and clearly an assumption you made. First, whenever we are calculating a pH of a weak acid, we assume that its dissociation is negligible or it does not dissociate. And for this also, because it's a weak acid, so you have to use the Ka from the data booklet. I will explain the idea how it should be done. So if it is an ethanoic acid, so ethanoic acid will be CH3COH and it will dissociate into CH3COO negative and H positive. So if we write, if original concentration is 0.1, this will be 0 and 0. But this is initially, the beginning. At equilibrium, the concentration of this one is X, this one is X. So this will be 0.1 minus X. If we write the Ka, the concentration of ethanoate ion, the concentration of hydrogen ion, and divide the concentration of acid. The Ka will substitute from the data booklet. We'll use a data booklet, we'll substitute Ka. What about the concentration of acid? Even though it should be 0.1 minus X, but what we consider the 0.1 minus X is approximately equals to 0.1 because the X is very small or negligible. So we'll have this value as well. And this one is X. So what will the formula here? The Ka will be equals to X into X divided by 0.1 because we neglected that. Or we can also say 0.1 into Ka into 0.1 is equals to X square and then take a root, we'll get the value for X. And the value of the X is same as the hydrogen ion. And from that hydrogen ion, we can work out the pH by using a formula, the pH equals to negative log of hydrogen ion concentration. So just you need a data booklet to get the value of Ka. This is always the way whenever you want to work out. The ethanoic acid Ka is 1.7 into 10 power minus 5. That's a Ka for ethanoic acid. So we'll have that as well. We'll work out hydrogen ion. And from hydrogen ion, we can work out the pH of the solution. If it was a strong acid, then the initial concentration will be same as the concentration of the hydrogen ion. If it is a ratio is 1:1 for hydrogen ion, it will be same. And what is our assumption? Always remember the assumption for calculating weak acid and weak base, that we assume that like the acid does not dissociate too much or there is no dissociation of acid. And all of the hydrogens which are here in the weak acid, like dissociation in case of a weak acid, are from the the dissociation of the weak acid is responsible for production of hydrogen ion. Because water molecule can also dissociate, which can also contribute to hydrogen ion concentration, but we assume it is not dissociated. So two assumptions. One is all the hydrogen ions from the acid and the dissociation is negligible or initial concentration is same as equilibrium concentration. Next is a titration curve. Yesterday we did about the titration curves. Remember the vertical part for different titration curves. Example, if it is a strong acid and a strong base, It was from 3 to 9. Now here, draw a titration curve showing the pH when a 0.1 mole sodium hydroxide and ethanoic acid. So what is this titration curve? This titration curve is for weak acid. Like as you can see, the acid which is used is a ethanoic acid, and ethanoic acid is a weak acid. So we have a weak acid and we have a strong base. So whenever we have a weak acid and a strong base, so what should be the range? If you see the titration curves for a weak acid and a strong base. So this is a strong acid, weak base. This is a weak acid and a strong base. And this part is a buffer range. Why it's a buffer range? Because you have a mixture of a weak acid and its salt. So that's why this region is a buffer range. Vertical part is from 7 to 9. So same way we have to draw. And we have to work out the equivalence point as well. The ratio between equivalence point means when the mole ratio and volume ratios are same, that we call as the equivalence point. So if it is a sodium hydroxide is reacting with ethanoic acid, which is CH3COH, and sodium hydroxide. So sodium will take position of a hydrogen. So it will form sodium ethanoate plus water. That's a balance equation. So ratio is 1:1. So, and the concentration is same. When concentration is same, the volume ratio will be equals to the mole ratio at equivalence point. So sodium hydroxide solution was added to 25 cm cube until the volume is 50. So at equivalence point, like because we use 25 cm cube of ethanoic acid, so at equivalence point it will be 25 because the ratio is 1:1. So first we identified that equivalence point should be at 25. Sorry. So at 25 we'll have an equivalence point, and for a weak acid and a strong base, the vertical region will be 7 to 9. So from 7 to 9, we'll draw a vertical. About 7 to 9, we draw a vertical. And because it is a strong, like sodium, and in a conical flask, as I mentioned, sodium hydroxide is added. So the original solution was acid, ethanoic acid, and then sodium hydroxide. So final solution is sodium hydroxide. So finally it will be 13. And originally, because it's a weak acid, so we can start with 3. So it's the same graph we'll plot. Then we'll have a buffer region here. And then we'll have so these are the points we included. Like a vertical region is there. So important part is this, like when you draw, so you have to learn like which region you will have the vertical point. So for a weak acid and and a strong alkali, you can have this word. Even 6 is also acceptable. You can draw from range. You can draw like it is, and the original pH of a solution which we calculated was about 2 or 3. And the vertical region, we started like example from 5 ranges there. You can start with 6, you can start with 7, or you can start from even 5 to 7 is also 5 to 10 is also fine. Is it clear, the plotting of this graph, how we sketched?
Yes, sir.
Yeah.
Okay. Then the next part is select a suitable indicator for this titration. So suitable indicator for the titration, What should be the suitable indicator? We always select a titration indicator according to this vertical region. So it's from 7 to 9 or 7 to 10 you can take. So for that you have to check a data booklet, because in a data booklet different indicators have different pH range. So we want an indicator, because which indicator is suitable, as we example mention a range. Let's say we are looking for an indicator which can show a color change from 7 to 10. So means either one of the limit, either both limits should lie within this range, or one is in the range, one is out of the range, or one is on the upper range and one is out. Like I can select any number, any indicator which show a color change from 6 to 10, or one of the range will be above 6, another one is below 6, or one of the range is below 10, another one above 10. That is because the best indicator which show a color change in this vertical section. Example, if I use a phenol red show a color change from 6.8 to 8.4. So I can choose that. If I use thymol blue is having a pH range from 8 to 9.6. So yes, I can also choose that. If I use phenolphthalein, it changes from 8.2 to 10. I can also choose that. If I use thymol pathylene, it shows a color change from 10.3 to 10.6. So I can also choose that. And if I select, like example, thymol blue, it changes the color from 6 to 7.6. So I can also choose that. Like there should be overlapping should be there. But if I, for example, if one indicator show a color change from 4 to 5, I cannot choose that, because that will show a color change in this section. We want one range to be in and one range to be out. Is it clear? Selecting an indicator for the titration.
Yes.
Should there be an explanation for the answer?
No, they did not just justify your selection. You will mention, like you will mention about the range according to the, and then mention that it is lying within the vertical region. Like the limits, yeah, vertical jump of a titration curve, it is lying. The answer is like select and then say let that is completely lying within the vertical jump or titration curve, vertical region of titration curve.
Okay.
Then ethanoic acid and trichloroethanoic acid. For this, you have to use a data booklet, because the one which is having a higher value of a Ka will be a strong acid. So actually, trichloroethanoic acid is more having a higher value. So this will be an acid, and this will be a base or alkali. How I worked out, because I know the Ka for a compound CCl3COH is higher than CH3COH, and you will use a data booklet in exam, the one which, and then it means this should donate proton. So this should donate proton and this will accept. So we'll have CH3, COOH2 positive will be there, and then CCl3, COO negative will be there. And what about the conjugate acid and a conjugate base, as we have to label? So this, because this was a base there, so here it will be a conjugate acid. And this is a acid here, so it will be a conjugate base. But we'll write conjugate, instead of just saying base, we should write conjugate. Or you can also say this is acid 1, this is acid 2, this is base 1, and this one is base 2. Or use the term conjugate. I prefer use conjugate rather than base 1, base 2, or acid 1. So for a reverse. So how we worked out? We worked out by comparing the dissociation constant value or the Ka value. Is it clear, this one? These are some questions related to acid-base equilibria. Next, we will start the organic chemistry next session, inshallah. Any question or doubt related to the class?
No, sir.
No, sir.